Hi everyone, how's it going? Let's get this thing started. I'm just gonna kind of launch right into it. I'm just so happy that everybody is here and chose this session um, over everybody else's. I feel like looking at the presenters at this conference and you coming here, you chose, between a dry age steak in some cases, and this one's kind of the chicken McNuggets type of presentation. But somehow you're here of all the choices, and we're going to talk about modeling. Here are some of my things. This book here, Just Tell Them, was sold out for a long time, and it's my first sort of main book, although I've contributed to other books, and it's making its rounds. It's all about a lot of the content we're going to talk about today. If you take a look at Progressively Incorrect here on your screen, that is my podcast, and it's quite a production. I'd love for you to join that community. It's what I release episodes every week with guests that are at this conference, by the way. And then finally, if you go and take a look at Step Lab, that is a platform for instructional coaching that I'm the director of Step Lab North America. And so if you want, we're going to be looking at some videos in this presentation that come from Step Lab, videos of children and of teachers doing modeling. So if you need these slides afterwards, I highly recommend you check out the presentation notes of this conference. They're all in there, updated. These slides, you can get them there. So let's dive right in, shall we? Here's what I would like you to do. I'm not seeing a terrible amount of screens on, but in a moment I might ask you to do your screens on. I'd like you to take out a piece of paper and a pencil. I have myself a mini whiteboard here that I'm going to be using for this exercise that we're going to launch ourselves in, and I have my marker. I'll just give you just a moment to get your materials all set up, and if you want to turn on your cameras for this, I would highly appreciate seeing some faces. But get your pencil and paper out and be ready. Hi, Travis. I know you from Twitter, I think.
Yes, good to see you.
And, Ms. Dickerson, what's your first name?
Carmen, Carmen.
Carmen, nice to see you there. It's great to see you. All right, we have our pencil, we have our paper. Here's what I would like you to do. I would like you to do this thing on your screen, please. Draw a dragon for me. Any dragon, how you picture a dragon. I want you to just draw it on your paper. I'm going to give you just a minute and a half, and I'll try not to talk. Go ahead and draw yourself a dragon, please. If you're just arriving just now, I've had everybody take out a piece of paper and a pencil and go ahead and draw a dragon as best you can on a piece of paper. Just 30 more seconds. A simple line drawing is okay, but do your best. Oh no. Okay. 10 more seconds. And I'll go ahead and I'd love to see. I'm going to go ahead and see if I can get all those tiles going here. I'd love to see some dragons here. Go ahead and show your screen what you did right here. Oh, look at us. Look at Travis, you cheater. And Jennifer, that looks way too good. Uh, but for the most part, y'all's looks like mine without even trying. I've never done a dragon before. Now, aren't we great? I'm gonna go ahead and I'm gonna share the point of this with you, which is what I've just had you do, obviously, was just not I didn't provide any instruction, essentially. I said, go ahead and do something that's relatively hard. I think dragon is probably one of the hardest animals, mythical creatures you can draw, right? It has haunches, and I'm not a very good artist, it has scales, it has all of these different things. Um, I would like you to try again. So find another piece of paper or just right next to it or just below in some other space. I want you to draw a dragon this time, but I want to draw you to draw a dragon after and as I provide a model for what this is. Okay, so here we go. This is the first thing you're going to draw on your paper. Go ahead. I'll do it with you just so I can time it correctly. And go ahead and add that. And here we go. And let's keep going. And keep going. And let me see. Now there's a little bit of extra detail here, as you can see. And they're going to have you take away some of those extra lines if you can. I have a little whiteboard here. It's super easy for me. You might want to erase. And go ahead and show me your dragon this time. Let me see how they're looking. Get the cube up. Oh, look at our cute dragons. Now, I want you, if you can see me in your very small screen, um, I want you to take a look at these two different dragons here that I've drawn. One, one looks different than the other, and I've never done this exercise before, but I've sort of changed the animal a few times. Um, the thing is that I think we all intuitively understand uh why modeling works in the first instance. And I think we understand why it's so powerful. Um, However, in math, modeling, I believe, gets a bad name. It gets a bad rap. And in fact, with modeling, um, we see full books, we see full areas of schools of thought in math in which we're criticizing or ridiculing modeling as not being a great instructional tactic and not useful really in any instance other than as a last resort for teaching something. Um, and I find that funny when you consider like how modeling, appears in other domains, like in art, for example, the importance of the expert and the master craftsman working with a novice in an apprenticeship type of role. In PE and sports, we think of the coach and how vital the role is, an active expert in that domain, leading the learning and teaching folks, especially when they're just first learning the skill. Um, and so on as we keep on going, right? We think about other domains and other areas. We think about how modeling is involved in every aspect of what we do throughout the workplace. Like when I was working as to learn how to cook when I was at a restaurant, what did I do? I was not allowed to just immediately start cooking. I had to watch someone else maneuver around the kitchen and teach me one thing at a time through a step-by-step process at which some point in time I was able to cook one thing for customers by myself and so on. If you keep on going and you think about all the different domains and subjects in which modeling has just an important and vital role, and then you get to math, right? And apparently math is not, it's not real. It's not real to be, to learn math in this way. You might know the books that I'm alluding to, that the first chapter is all about mimicking, um, that somehow modeling is copying. And in fact, as I will argue today, and as I believe the research demonstrates, modeling is an incredibly important tactic for teaching folks new things. Um, so how does modeling work and what's the evidence base behind it? The main area I'd like to point your attention towards is something in the research that's called the worked example effect. And what the worked example effect is this. In one group of participants in this type of research, the students do not receive a model. They are doing the dragon thing that you just did, right? They basically are given a problem like 1/5 plus 3/4. They are screened ahead of time to make sure they do not know how to solve this type of problem. So they are novices, and they are asked usually to do like 12 of these problems. Maybe they're given 12 trials or 10 trials with different numbers, but the same concept, the same type of procedure. In group two, the students receive both models and problems to solve. Not so they get more information. They usually get 6 models and 6 problems to solve in alternating fashion, is the typical way they do this. So I get a model like this that shows me step by step how to do it, a worked example, how to work this type of problem. And then I get a problem that's just like it with different numbers, and I have to solve it myself, and back and forth just like that for 12 trials. What happens when we do this type of research, which has been conducted since at least the 1980s and until now? My dissertation happened to be with worked examples, looking at different ways that kids choose to use them, for example. But there have been so many studies, and worked examples expand now beyond math. Even though they just began in math, there's worked examples for science and for English. There's a great paper about how to work a Shakespearean text for kids through a worked example so they understand what the text means, right? Models. What happens in this research? What typically is the result? Well, the group that gets the models tends to learn the material much faster. They usually learn it earlier in the trials. They're able to confidently perform the procedure or follow the process pretty fast. They also report lower levels of cognitive load or lower levels of effort. So it's a lot of bang for your buck. Not only do they learn it earlier in terms of time spent, they report it wasn't as hard to learn it, which is great, right? The other thing that we end up finding out is it's just more effective to give them the models. You give them the model, and at the end, at the delayed test, 2 weeks later or so on, the student has retained the information better when they were given the model. When they're not in the modeling condition, they may have figured out how to do it like through trial and error. Uh, but they don't remember the trial and error process. This is a lot like if you think about like my dad is terrible with technology, and he will say, Zach, you need to come over to my house and come fix my computer. And I'll say, okay. I drive to his house. He has figured out his problem on the computer, and I ask, oh, what was the problem? And what was it? What did you do? And he says, I don't know what I did. I just fixed it. It just works again. That's what happens when you're just given the problems. When you're given the models, you know what you were doing because you had, just like we had with our dragon example, you had a guide. You had a guide to understanding what you were meant to do and how you were meant to do it. And finally, newer research. This just came out a couple of years ago, but it's backed by other research around sort of affective measures. Research shows that uh, it's emerging. I'm not saying it's bulletproof. Some research coming out is suggesting that giving students the worked example or the model decreases their feelings of stress, anxiety. It may increase their feelings of self-esteem. And you have to ask yourself why. Why would that be the case? Well, it's because the students feel supported. They feel like in the research that they weren't just making stuff up, right? That there was a sense of systematic support, that you can always rely on models to learn the material, rather than maybe this is me. Maybe I'm supposed to know this. Maybe I'm not smart, right? Is a feeling that you get when you're not successful doing something, especially if you don't know what everyone else is doing and you start to make comparisons to other people. You start to feel like, is this something I should already know and I just don't know it? And this is a problem with my math ability. This is very different than what we're often told in the math realm, which is that if you give kids a lot of opportunities to try to struggle and try to discover and figure out, that in fact that will actually bring them joy and reduce their anxiety around math, when the opposite is probably the case, right? If you're not supported with good, effective, efficient instructional tactics, you might start to blame yourself and start feeling like this might be a me problem, not a math problem. Or you might start externalizing blame and you say, it's math. I'm not a math person, I suppose. And now we're in the realm of sort of self-blame, and it's just a it's not a great way to learn. Is just like my dragon example. It's not a great way to learn. You a much more effective way, the worked example effect tells us, is to provide a healthy diet or dose of models. Y'all might be on the same page as me, but um let's keep going. One of the areas of research that sort of emerged from studying worked examples was a body of research, a collection of studies and recommendations, a framework, if you will, called cognitive load theory. And cognitive load theory is it's based on a very simple premise. It's that, and a very uncontroversial one, to be frank, right? We know that all students are endowed with a working memory that is very limited. It can only handle just thinking or processing just a few items at a time. And then students also have this long-term memory, and long-term memory is where all of our facts, knowledge, skills, experiences, where all that stays to be retrieved at any point in time, but it's not the thing we're consciously thinking about. So, working memory, right now, you're working with the things I am saying, and you're analyzing this slide and you're processing it in your working memory. Long term memory is just where you keep all your math. Or when I say, like, what was your favorite song during high school? And you say, oh, yeah, I don't know what my favorite one was, but the most popular one was definitely Usher's Yeah. And you go, oh, yeah, that's right. And you start to retrieve a cascade of associations around that song and where you might have been when you heard it and who your friends were and what you might have been wearing. All of those things are sitting in your long-term memory. And so the problem is you give students a problem like this that they don't know how to do, and they're forced to essentially use a process called means ends analysis. This is just random trial and error. You get a problem and you just start messing around with it. All of us have experienced that feeling of trying to mess around with a problem. Like, for example, if you've ever had a plumbing problem at your house, there's water gushing out, and you go and you try to fix it yourself with some tools, what happens? You're using trial and error. You have no, unless you're a plumber, of course, but I'm not. You're using trial and error, means ends analysis, trying to figure out how to stop the water from gushing, turning things and twisting things. And you might be making things worse. You might slowly be making your way towards the goal, but this isn't productive by any means. You don't learn much from doing this because of how random it is. You might solve the problem. There's this thing called the infinite monkey theorem, which is basically if you give a monkey a typewriter and say, write, and you give them infinite amount of time, the monkey will eventually um, write Shakespeare, right? Because infinity allows for that possibility. But how often will a primate write Shakespeare, at first try? It will never happen. And it's the same thing with humans. Given enough time, we can solve this problem, but it is so stressful and there's just so limited time in the curriculum. And honestly, you might not even know what you did and how you did it, just like my dad. And so then when you finally do solve it, you don't even remember the process or the procedure you used. You might have made up a really inefficient one that later is going to be a misconception that's a barrier to you solving this problem. So, really, because we have this limited working memory, and the goal of education is to get math into long term memory, um, this is a very inefficient way to teach. It's a very ineffective way to teach. And I can go ahead and test y'all's working memory right now. It's a very simple procedure that if you want to do this with your students, I really encourage it because it just kind of shows them the way of why do I forget stuff? Why do things slip out of my mind? Why do I have a hard time retaining every single thing the teacher is saying? It's because working memory is this bottleneck, this like wine bottle type of metaphor in the mind that is preventing a lot of information from being held onto in mind at one time. So here's how I'll test your working memory. In this little space right here, I'm going to put some numbers, and then I'm going to ask you all to repeat them back. However, I don't want anyone to write them down because that would be offloading the information out of your working memory onto a piece of paper. I don't want you to type it down. I just want you to remember them with the working memory that you have. Okay, here we go. A string of numbers right here in the center here. And let's begin. Okay. Now, that might have felt quick. That was on purpose, right? And right now some of you might be rehearsing these numbers in your head. You might be trying to keep them in mind. The more I talk, the more I distract you, the more that I'm introducing new information. That when I say things like when I was a kid, my phone number was 253-475-6314. I'm interfering because I'm introducing more information into your working memory. Some of you might be using a strategy at this point. You're trying to chunk the numbers into groups of 3 or groups of 4. That's because your working memory can only handle so much. So you're chunking them into meaningful or memorizable chunks so that you can keep those chunks in mind at any, so that you can produce this. Uh, Go ahead and in the chat, I'd like you to put the string of numbers, but instead of putting it forwards, I want to see you put it in reverse order. Put in those string of numbers in reverse order into the chat. Let me see if anybody's got it. We've got some discrepancies. Now, look at all these different ones. Some people are like, nah, I don't remember. Now, maybe if you did get it, maybe Patton will send you a free t-shirt. I don't know. I want a Patton t-shirt. Where's my Patton t-shirt? Um, but here's the string of numbers right here. Just let's go see if anybody kind of got it. Oh, Alicia, you were so close. You were so close. But Christy, I think you got it. I don't know. Lisa, you know, people have been talking about the patent shirts for some time. Um, so the point is, though, all of our working memories eventually reach a limit. Math. Why is math so much harder than every other subject, it seems? At least it seems like for our students. Why do they hate it sometimes so much? Um, this could be the reason. Math involves very cognitively demanding material that includes more than the number of elements that can usually be processed in working memory at a time. And not only that, the elements cannot be thought about in isolation. You give a child a problem, and they can't just think about each of the elements independent of each other. Like the periodic table is something is that you can think about those elements by themselves. You don't need to know the other elements to understand each element. Where in math, the element interactivity is the actual term for this. The each of the steps of the procedure and the concepts all rely on each other because math is relentlessly hierarchical. And so you have to deal with so much in mind as you work a problem that it essentially overloads your working memory very quickly. Math is a complex subject with material that is highly cognitively demanding for a reason. And it's because of this, we need to design our instruction in a way that honors the cognitive architecture of each of the kids in our classrooms, right? The thing that they're born with, right? So when I give a child a model, if you think about the worked example effect, when I give a kid a model, what am I doing? How is this benefiting them, right? Well, the first thing is that it reduces that whole means ends analysis or guesswork that kids would do. It reduces the problem solving search. So I'm thinking, oh, maybe this will work and maybe that will work to get me towards my goal. I plug in this number and I plug in that. That doesn't work. I don't know. I don't know if the problem's shaping up the way I want to. When I get a model, essentially that problem solving procedure um, is eliminated, so I can just think about how the math works. I'm directed in a very productive way to learning the math versus expending all of my limited working memory resources to trying to guess and check and solve a problem that I do not know how to do. That guess and checking procedure, by the way, that means ends analysis, you do not need to teach kids how to do that. It's something we've all evolved to use. Crows use this problem solving procedure when they're trying to open up an acorn, right? Dolphins use this procedure. It is simply, what is my goal and what are some things I can do to try to get me towards that goal? It's not something that needs to be taught, because if we did not know how to do this, we would not have survived as a species. What does need to be taught is the math, because math is not something we have evolved to know just intuitively. So that's why modeling is so effective. That's why it's recommended in so many guidance documents. It's why when we hear things like modeling doesn't work, um, with no research evidence to back it up, just some dude's opinion about it stops you from thinking. It's nonsense. It gets you thinking about the thing you're supposed to be thinking about, which is the math, where random trial and error gets you thinking about random trial and error. And they already know how to do that. Everybody knows how to slap a hammer or a wrench around underneath a sink. Not everybody knows how to fix a sink. So that's kind of the absurdity. To sort of illustrate it even further, John Sweller has this quote that I love. He says, "A problem that we either cannot solve or that would take us weeks or months to solve may be solvable in seconds if someone shows us how to solve it." That's the other element of this, is that doing trial and error type of problem solving, means ends analysis, will inevitably take a lot longer, and there's no time to waste, especially for the kids that need our most support. The kids who need more trials to learn anything, we have to pick the method that is most efficient to give them the most practice opportunities, to give them the most opportunity to learn. The kids that maybe are teacher proof, they can learn maybe through guessing and checking. Um, a lot of our kids, it's just an inequitable means of teaching, is giving lots of productive struggle type of mathematics tasks. Um, so with that, I would like to just kind of outline some of the areas in which you should be thinking about, in my view, around modeling, like what makes effective modeling. Because obviously, there's very ineffective modeling out there. There's teaching that involves a lot of continuous talk, where the teacher is just saying lots of extra words that don't help the students. There's a lot of modeling that may embed misconceptions. There's a lot of modeling that simply it's the teacher doing all the heavy lifting. I like to think of that type of modeling as like a GPS. A GPS will get you to your destination, but by the end, you do not know what you did to get to the destination, because the GPS was doing all the thinking for you. We have to do modeling in a different way than a GPS style, where the student is recruited to think about each of the steps and each of the legs along the way. So there are effective ways to model and there are ineffective ways to model. What can we rely on when it comes to the evidence? That's what the next part of this talk is. Here are some of the things we can rely on. I'll give you a chance to study your screen. Now, of these kind of buckets, which of these is most interesting to you? Which do you want me to focus on most heavily? Go ahead and plop that in the chat. I'd love to get a little bit of a little formative assessment opportunity. Go ahead and type into the chat which of these you kind of want me to emphasize the most. Oh, I love it. So many people put in examples that I kind of wish I had built out that space even further. But hey, I'll give you my give me my best shot. Um, so let's get started, shall we, with the with kind of components of effective modeling, what the research implies. Research can never tell us what to do specifically, but it can give us guidance in terms of best bets that we can use to do any tactic or technique, including when to use it, for how often, for and using certain key features. Let's dive in. So the first thing I think um, is very obvious, but because it's obvious, it's not very good advice. It's not very good advice to tell somebody you should have been clearer in your modeling, in your explanation, because if they had already wanted to be clear, they would have been from the start, right? Um, but so we kind of have to operationalize that just a little bit. The first is to know that, like, in terms of the meta analytic data, the meta analyses around clarity, the teacher clarity is a very is associated with learning gains, right? Students learn more, they're more satisfied with their learning. Um, so if I go ahead and I start off my lesson using this text on the left, which is like, in the research, this is the unclear condition. It includes lots of things like uh, false starts, hesitations, what researchers call mazes, where the teacher is kind of going in between and back and forth between different ideas, not really committing to one, just like being in a hedge maze, right? Um, maybe the presentation is just not very fluent. It's not very confident. It's not said with the fewest words possible. Um, this imposes an unnecessary cognitive load on our working memory. There's just more information that we need to deal with that is distracting, is diverting. It's hard to kind of deal with and process in working memory. Much better when we look at comparison kind of studies is explaining things in the fewest words possible. I call those minimal statements. When you're teaching and I have my whiteboard up and I have my marker and I'm ready to go, I'm thinking through a script that is just a series of very punchy, crisp statements that only say the things that need to be said. If I'm going to start talking about, for example, denominators and numerators, I'm not going to go in and out between the bottom number and the top number and denominator and numerator. I'm going to keep my wording precise and use the same terms every time. This goes back to, like, really effective instructional design, like, for example, with direct instruction, where the language is just faultless. It's just how it should be. And how do you get to that point? Well, this takes a lot of practice with your subject, but it also could take just practicing in front of an empty room, right? What is the most efficient way to get there? When I talk with teachers and I have them script out what they would say to teach a math problem, they often can cut out up to a third or two-thirds of the extraneous language that's in their explanation. Their explanation just includes a lot of side stories and diversions. Cutting these out helps learners to process the model much more effectively. That's why on the screen you can see that down arrow. It frees up working memory to attend to the math rather than attending to the unnecessary extraneous wording that's not precise enough, that isn't specific enough, that meanders and goes off on tangents. um Important really to think about, like, what is relevant to learning this material. Is this something we need to say now, or can this be left off to some other time? um Research showing a lot of different kind of extraneous forms of processing. For example, having like a GIF on the screen sort of just like supports this idea. The idea that having extra things on your screen that are not necessary, the learner has to attend to that and has to attend to what you're saying. So really getting rid of anything that is fluff, as Anita Archer would say, cut the fluff so that you can teach the stuff more effectively. They've shown studies with, like, animations that are, very distracting. What does the student attend to? They attend to the distracting animation. They don't attend to what the teacher's saying. I'll block that off because it's so distracting. But one of my favorite studies is a series of studies by Richard Mayer and colleagues. And what they do is they give one group of students a science text around lightning formation, how lightning is formed, and the other group, they get the same science text, but they get videos and images of airplanes being struck by lightning, of people being rolled out on stretchers because they were struck by lightning, ambulances, and so on. Really exciting stuff, I suppose. They call these seductive details. They seduce the learner to commit their cognition to things that do not have to do with the science. You can all predict what happens in these studies. The the condition, the treatment that gets all of this exciting, entertaining stuff on the sides, they learn a lot less science. It's the same for anything. When we're teaching, we really have to be very targeted around what we say and how we say it. And I think of this one teacher I had who, and we've all had this teacher who just explained with lots of anecdotes and tangents, going off on sidebars that had nothing to do with what we were learning. And of course, what we would do is we would sabotage his lessons as students by trying to get him to tell stories. Like he had this farm, he had lots and lots of problems on his farm all the time. He'd be teaching about I don't know, Punnett squares, and we would say, Mr. Dykman, did you ever have bees on your farm? Did you ever have wasps on your farm? And then he would go on for 30 minutes talking about how he eradicated a bunch of wasps the other weekend, right? These stories don't help, they hinder, right? And I mean, one of my favorite stories for when I was teaching had to do when I was trying to teach a Venn diagram to students. I taught fourth grade for 14 years. I write a Venn diagram up on the screen, and then I notice my kids are kind of seeming a little bit bored. So what did I do? I said, "Hey kids, doesn't a Venn diagram kind of remind you of a butt?" And I lost them. I lost the kids because I had introduced something that I thought might bring them some entertainment, and really it was very distracting. All the boys are standing up and shaking their tailbones, and the kids are just jumping up and down laughing every time I write on the Venn diagram. Uh, the message is very simple. Be very deliberate, very explicit, and very precise about what you put into working memory when you're modeling, and to be extremely careful, overly careful about the teacher wording, because otherwise you might confuse them or distract them more than teach them, right? Um, it's very related to this idea of sort of precision in language would be the precision in what you put on the board, what you actually have students attend to in terms of visuals. Some of my favorite studies of this involve this exact lesson right here. I'll give you a chance to read it. Read what the teacher is saying here at the top. Now go ahead and in the chat, guess what this lesson is about on the basis of this text. Go ahead. Oh, we have some good guesses. That's okay. That's okay. Nobody's got it so far, but very close. Bee Shields, you're the closest so far. Actually, what it is it's a bicycle pump. It's how a bicycle pump works. And there's more to it. There's more to the lesson. But what this image on your left illustrates is that how taxing just talking is when it comes to learning. Uh, Much better and much more effective is to simply pair what you're saying with a visual demonstration or process of what you're teaching. This is the worked example in math, right? And in the case of this science text, it's this diagram. Um, Having a concrete reference for the students to attend to is vital for them being able to pair what you're saying with what they're meant to do. All of this is obvious. Nothing I'm trying to bring to you is inherently innovative sounding. It it's these are just principles of explicit instruction, right? Whenever possible, pair what you're saying with what the student is meant to do themselves, right? In math. Um, Unfortunately, there are a lot of caveats that come with visuals that I think are really interesting to explore. One of those we've kind of touched on, which is that don't introduce things in the visual environment that clutter the presentation, that are not helpful to learning, right? So, just like in our language, in our wording, we're going to cut out as many of those sort of tangential and irrelevant type of words in our speech. We've got to do that with what we present on the board. I'm a huge fan of document cameras. I simply just have a piece of paper. I like the precision of the pencil, and I'm just slowly populating the screen with just what the student needs to see. And not adding in extra things. I see a lot of times departments create centralized PowerPoints. That's great. But all this extra branding and side stuff and just fun visuals that are meant to entertain, they probably don't teach very well. Now, speaking with visuals is very effective. This is the multimedia principle of cognitive learning. Um, but having lots of extra text on the board is not very helpful. There's a reason for this. The student is meant to attend to what you're saying and the diagram or visual, and then they're meant to also read this text. It's a redundant source of information. They really only need you to talk and present over the visual. The extra text doesn't serve; it actually hinders cognition in many cases. Some exceptions include small captions, or you can just pause and say, "Everyone, I would like you to read what is on your screen." But what you're doing there is getting rid of the speech so that there's not a redundant modality that has taken place at the same time. Very careful that when we're speaking, that what we say matches what's on the screen. Images and speaking are great together. Having extra text that replicates what you're saying is just unnecessary and hinders learning, right? And I mean, again, in the realm of obvious, of course, but having a signaled presentation where you are pointing and deliberately showing the parts of the math that you are working as you go, it directs attention to the parts they should be thinking about. Where an unsignaled presentation doesn't do that. I see a lot of teachers oftentimes they're circulating, they're going behind the students, they're going back and forth, and the kids' necks are moving like they're in a tennis match. Being very precise with our pencil, with our laser, with our finger to pair a signal with what they're meant to be processing is an important principle of this. And then finally, um, my favorite, of course, having great visuals is important, but there's emerging evidence that if it's already drawn on the screen, like you already have a worked example up, the student now has to look up and down and around the worked example. It'd be much better if you just progressively added to the example. So you work a problem on the board and you just do one thing at a time as you talk. This directs attention to what you're saying, and it doesn't make the eyes go scatter around the worked example. I see a lot of teachers in math in particular, they're like, yeah, okay, I heard about worked examples. Here's a worked example on the screen. And I know there's just too much information on the board for the students to learn from it. Much, much, much better would be to use animations or to simply draw it on your document camera and slowly populate it rather than presenting it all at once. It's just a lot of information to take in at once. Um, so with that, I mean, I think about like all these different tools that teachers have at their disposal. There's PowerPoints and whiteboards and document cameras. I have my preference. What are some of the benefits and drawbacks of each of these tools? Um, Now that we've kind of dove into some of these modeling with visuals principles, go ahead and type those into the chat. Which do you prefer, and what and why? What benefit does it give you when it comes to teaching your subject or teaching math to your kids? You know, it's funny. It's funny. I see so many dot cams here. And I recently went to a school in which every teacher was purchased a dot camera and only the math teachers were using it. It was very confusing to me. The other thing that was even more confusing is that the architects had designed it so that half of the rooms, the dot cam was in the back of the room. Well, what's going on there? Now the students are missing out on the nonverbal cues, on the facial expressions, on the gestures from the teacher, and they're not attending to the whole presentation. They only get the benefit of just a hand working the problem. So, and the teacher really can't look at the kids in the eyes and use their expressions as formative data to, are they confused? Do I need to slow down? Do I need to adjust? All half of the rooms, just by the convenience of the architect, had the document camera on the exact opposite side of the room, and half of them had it in the front. So who used the document camera? Those that had a document camera in the front, right? That's the sort of the absurdity of like how education is often just led by people that do not know how to teach, who are not teachers. Um, Regardless of what you use, I like PowerPoint for this purpose because it saves all of my work, right? I have all of my do nows are all on PowerPoint so that I can have a running record of all of my do nows and I can go back in and out. I can also share do nows out with colleagues when it comes to and resources with colleagues when they're on PowerPoint, but they don't give the benefit of live modeling, of drawing step by step. That the dynamic drawing principle of multimedia learning is so persuasive that I sort of use a hybrid now of PowerPoint and dot camera. How do I do that? Uh, Basically, if you use your keyboard shortcut and you just press W, I'll press W here. The PowerPoint just turns white. If I press it in, it comes back. If I press B, it turns black. So what I will do is I have something up on the screen. I press B to make it black, and then I work a problem on the board, or maybe it's on a different part of the room, and then I bring it back. That way the students don't have their attention split between different sources of information, right? If you learn nothing else in this presentation, you now know that you can press W or B and it will turn your PowerPoint screen a single color, which can help with attention, right? Um, let's move on to talking about alternation or interactive explicit teaching of teaching in very small granular steps. Um, we know that working memory is a limited structure, but everything needs to be attended to and brought into working memory in order for us to process it so that it can go on into long-term memory. Working memory is like that bottleneck that prevents a lot of learning from taking place because we have to slowly, step by step, spoon feed a little bit of information at a time. Otherwise, it's not going to stick in long-term memory. I'll put a text up on your screen. I'd like you to take a look at and try to make sense of it. Now, how much of this do you think you'd actually retain? Uh, there's just a lot of information. Imagine a teacher is saying this kind of in an extended lecture type of format. They're presenting and talking and explaining, and there's just all there's all of these facts coming in to working memory. The chances of retaining anything are very small. And the main reason is because they don't have prior knowledge to bring to bear to learn this, and it's too much information presented at once. Um, we have to break this kind of thing down. I was in a very interesting situation at a brain conference in which in the audience was someone who was actually an expert in convolutional neural networks, a neuroscientist, and they knew all about machine learning and all this other stuff. They looked at this and they said, well, yeah, obviously. That was their response to this because they had the long term memory resources to make sense of it. In fact, the researcher, the scientist, looked at this text and found an error in the text because that's how much she knew about the topic. You and I don't know much about the topic, so all of this presents a very heavy burden on working memory unless we break it down. And so, really, effective modeling and explanation and demonstration, effective instruction must be highly interactive. This serves a few purposes. When I alternate between me and you, me and the student back and forth, offering just a little bit of information, and then you have a chance to process it, answer a question about it, respond on a mini whiteboard, explain in your own words. When I do that, I'm just funneling one thing into that bottleneck of working memory, having you think about it, having you tell it back to me. And once you tell it back to me, I know whether or not I can move on or not. I know whether or not you thought about it or even listening, right? So much teaching, when you observe a lot of lessons like I do, proceeds with the teacher saying things and they don't even check if the kids are paying attention to it. Um, uh, and compare that, for example, with if you needed a kid to go do a task for you. For example, go home and get your field trip form signed. The teacher would always go like this: tonight, I'm having you get your field trip form signed. What am I having you do? You're going home and you're getting it signed. And who are you going to ask? Turn to the person next to you. Is it your mom, your dad, your parent, your guardian? Who are you going to get it signed? Turn to the person next to you. Okay, raise your hand. Who are you having your field trip form signed? Okay, yours is your mom, yours is your dad, yours is your uncle. Excellent, excellent. Tonight, you're going to get your field trip. What class? Signed. You would do that for something important, but oftentimes with math, we don't pass over the different segments of the model to the students. We just expect that they're listening. They're not listening, or we don't know if they are. We don't know if they're thinking about each of the parts of the thing we're talking about. Great modeling is interactive for both its formative purpose and for its behavioral purpose of checking for listening and attention, and also because of its working memory purpose, one thing at a time thought about at once, as opposed to lots of things having to be thought about all at once. So, some of the things that I've been working with schools, I work with dozens of schools around the globe actually, um, is arming teachers with just a set of techniques that really work in most circumstances, uh, getting away from hands up type of teaching. where only the volunteers are recruited to participate, where all students are meant to go 5 + 1 is 6, 5 + 2 is 7. That's right. Turn to your partner next to you. What fact do you need to remember? Excellent. Let's go. Now, mini whiteboards out, and we're going to do a mini quiz. Loads and loads of participation techniques that get every kid initiating active responses in an alternating fashion. Uh, it's very predictive of learning. It also serves to alleviate the burden of this material, which math is highly complex and it's relentlessly hierarchical. So step by step, atomizing the content with opportunities for the students to process each of those elements in a much more hyper interactive way than most classrooms operate is key. Is key. I'll show you some examples of videos. And we may, I'm looking at the time. I, of course, just rambling on and on. Well, let's watch some videos and kind of see how these teachers do it. I'm a huge fan of a video. I think what it does is it stops it stops all of us from imagining what the heck's going on and actually gets us to show it and see it. Let's watch this video that shows some mini whiteboards here.
Okay, here are your directions. Find the inverse. When you think inverse, I want you thinking reverse your x and y's. Rewrite your equation with the exact same thing written, except swap your x and y and hold up your board once you have that. Good, good, good. Rewrite it so that you have your x and your y in swapped positions. Good. Lamani, will you check in? Yep. Back up a step and swap your x and y. Yep. Very good. Just go to IP. Back up a step before you do anything. Swap your x and your y. Good. Yeah. All right. Boards down. Here's what you should have just written. Instead of y = 3x, when you swap it, you're going to write x = 3y. Your job right now is to isolate y. Once you have y isolated, hold your board up. What happened to your 9? Good. Kimmy, go to IP. Yom, go to IP. Turn towards me. The +9 is correct. Now you need to get y by itself, divide both sides by 3. Go to your IP. Good work. If you have no operation there, we assume it's multiplication, but you just wrote addition. Add 9 to both sides. Go to IP. Go to IP.
Thoughts on that video as I queue up the next one? Go ahead and write it into the chat. Now, Sabrine, Sabrine says, I love the instant feedback, right? I want you to take a moment to think about one of the most popular things that's going on in math education right now is vertical whiteboards on the periphery of the room, on the perimeter. And I understand their intuitive appeal. The kids are sitting often for too long. So this is an opportunity for them to stand. That's pretty much the only thing I like about it. I like that they have an opportunity to stand once in a while. So if you have the affordance of whiteboards on the perimeter, that might be a purpose is that they've been sitting for 40 minutes, they can stand for a few minutes it gets them up and moving, fine. Everything else about these vertical whiteboards just defies common sense when it comes to effective teaching. Kids are all sharing the same space. So that means only one person is writing at a time. One person is doing the work. We have many whiteboards in all classrooms. We could get everybody doing all the work. Everybody instantly in the math doing the work rather than waiting and passing a marker around. So what people that like this method tell me is they each have a different marker. Have you ever tried doing this? Go try it. And you will instantly see how frustrating it is. Kids writing over each other's writing using different colors, and who is doing the thinking? The kid who's the most dominant in the group, the kid who has the most social control over his peers, the kid who knows the most math. Who's the kid not doing any of the math? The kid that we got into teaching to serve. The kid who struggles with this type of learning environment, that struggles to produce math on their own. So what do? They wait back, they sit back, and they let other kids do the math for them. Not to mention everyone's writing on top of each other. Not to mention the teacher cannot go around the room and give everyone feedback. I've heard people that love these vertical mini whiteboards, and they say, I give feedback just as often as a teacher who does mini whiteboards. No, you don't. You're not superhuman. You're going one group at a time and giving them feedback. And by the time you get to the next one, the other group is done with what they have been doing. So they don't benefit from your next circulation of feedback. You need everyone doing the same thing at the same time on their own so that you can give instant feedback. And so you can assess, where everyone's going, and you give everyone equal shot at being able to do and work the math. Vertical whiteboards have a very small purpose and role in education. They do not deserve a whole book or rewriting how math works because they're so ineffective and inefficient for very obvious reasons, right? Again, I don't want to say that they have no role because everything can be used at some point in time, but they certainly do not merit a revolution in math education like some schools have undergone. Schools, by the way, that often see their scores tank right away uh, after implementing something that just looks really cool and groovy, and it doesn't really do the thing of teaching that we need. It doesn't give the kids the ingredients that they need. Let's take a look at this video, and
another one. Introducing some negatives this time. Be careful. Three, two, one. Boards down. Good, we should have got 2-1. If you did not get 2-1, the common mistake that I saw, boards off. We're going to try a harder one now. Wipe them clean. We're going to introduce some algebra into this. So it's going to get a little bit harder, but you just need to think about collecting your like terms like normal. Five, 4, 3, 2, boards in the air, 1. Beautiful. Fantastic work, team. I'm seeing 4 boards with the same mistake. Put your boards down. And again, our mistake that's cropping up here is with our negatives. Boards down. 4 boards with the same error. The same error again is with on.
First question for you guys. Ionic bonding occurs
so
between. Have a read, have a think. I'll give you.
So again, and I won't belabor the point. Again, when we're explaining anything, we have to start thinking about how we model it, how we demonstrate it, as being an alternation between the teacher and the student. Just a few very crisp and clear statements with an opportunity for students to respond, to process it, to make sense of it. And this has to happen, I think, at a very brisk pace. We're talking about planning out our questions in advance of what we're going to teach, checking for understanding very, very repeatedly, as you saw that last teacher doing. You wouldn't be able to get that type of feedback on your instruction without everyone doing it all at once so that you can locate the errors. We often, with certain schemes of teaching in math, we often make ourselves pretend like we're detectives and we're going around trying to figure out everybody's error. If you can see everybody's answer at once, you immediately know whose errors, who's committing errors. You can create interventions. You can see, where do I adjust? You can see, do I need to slow down? Do I need to do another problem? Should I take that problem and put it in my do now? Should I do a delayed test at the end as my exit ticket? All of these things are learned through constant alternation, choral response, mini whiteboards, turn and talks, lots of stop and jots in your notebooks, at a very brisk and bouncy, perky pace, so that you can get lots and lots of math, and the time just goes by so quickly. I'm looking at the time. So, examples. And I'll just whiz through because I know you've got a lot of things to do today, and we will end on time. Um, One of the things that I love about the research is when you get a funny example like this when it comes to examples. Imagine a teacher is in front of his class and he waves a green uh, piece of fabric over his head. And he says, "This is glurm." The number of interpretations for glurm are vast. A kid could think this is glurm means cloth. This is glurm. A glurm is perhaps green. Glurm is an action of waving. It's a waving cloth. It's a waving green, and so on. The combinations are quite, there's a limited number, but there's a lot. And this just illustrates, this is coming out of Engelman and colleagues' work with examples and non-examples, why one example is never enough to teach a concept. It doesn't allow students to generalize and intuit what it is, usually. So when we're teaching math, the important thing is to be providing lots of examples. I remember when I was teaching symmetry as a third grade teacher, and I gave an example like this. I give out a worksheet. I say, everybody, go ahead and draw a bunch of lines of symmetry. Just from this basis alone, what do you think they did? They all wrote vertical lines on everything. Vertical dotted lines down every shape, no matter what its orientation. Teaching needs to proceed by showing minimally different examples to illustrate where the math, where the concept changes from, yes, this is an example of it, to no, this is not an example of it. And as you go down and you see, like, the lines of symmetry are built, you start to be able to generalize the concept to other shapes. But you don't stop there, right? You have to give more examples and further examples where symmetry is not possible. A line of symmetry is not possible to be drawn. Examples and non-examples form like the basis of really good teaching. We often only give one example and then we give problems. That's the bottom line. Finally, the main thing that we want to make sure that we do with students is we want to make sure that we're not holding them in modeling land. We have to pass over the baton. If you think about our novice and expert differences, modeling in terms of worked examples is very effective for novices, and it slowly decreases in effectiveness as the student gains more and more expertise. And eventually we need to turn it over to them. We need to basically utilize a system of gradual release, of I do, we do, you do, that leads to the student solving problems independently. This manages cognitive load, and it's just so motivating to feel to feel supported. I was going to show you a video, but we do not have the time. Take a look here at what we talked about in terms of the buckets here. Which of these you think would be most useful to you as you go off and you teach your next lesson? And I really do appreciate you coming here. I just want to make a note that modeling in math is so important. It's part of effective teaching, just like it is in every single other thing in life. Math is not super special in this regard. In fact, math needs modeling perhaps more than other things because the information is so darn complex. I appreciate you coming. Thank you so much for attending my talk. I'll stay on for anyone who has any questions for me. Thank you so much.